I'll start over. Hi, everyone. Thank you so much for joining us today. I'm Kavya Elchuri. I'm a senior software engineer at Bloomberg. I'm on the platform as a service team.
I'm Sahil. I work on the same team as Kavya, and I've been with Bloomberg for about a year now.
So today we are going to talk about the journey of our platform's migration from NGINX to Istio. We are going to share our motivations, our migration plan, the experiences that we had, and finally the lessons learned. So before we dive into that, I wanted to quickly introduce you all to our platform. Meet BPaaS. We call it Bloomberg Platforms as a Service. It's a multi-tenant model to deploy Bloomberg services onto Kubernetes. We have thousands of applications and ingresses across thousands of tenancies. These are all deployed across 50 Kubernetes clusters. And our ingress gateways serve tens of thousands of requests per second. We'll next look at the motivations behind our migration.
So yeah, let's talk about where NGINX actually falls short for us. So as we scaled up our Kubernetes clusters, we started noticing certain performance issues with NGINX. And NGINX also doesn't have HTTP2 support, which meant that protocols like gRPC, which relied on HTTP2, were implicitly not supported as well. And cert management was another friction point for us. NGINX uses opaque secrets, which are readily not compatible with certain cert exporters. And finally, we were also limited by the lack of customization at an individual ingress level for certain HTTP configs. And the reason why we decided to move to Istio was because of the well-known advantages it provides us. Firstly, the advanced traffic management features like request mirroring, canary rollouts, and sticky sessions. It also has inbuilt support for modern protocols like HTTP2, HTTP3, and gRPC. It also gives us the ability to configure fine-grained access control policies between applications that are running on BPaaS and between BPaaS applications and other Bloomberg managed services. And also, as Kavya mentioned, we deploy our workloads across multiple Kubernetes clusters, but currently we are limited. Currently, the service discovery is just limited to the scope of a cluster. We'd want to move to a multi-cluster model where Istio can help us with service discovery across all our clusters. So now Kavya is going to talk about how we laid out our transition plans.
So what we started off with was an evaluation phase to ensure parity between NGINX and Istio. During this phase, we checked if Istio supports everything that NGINX does, and also checked if Istio overcomes all the limitations that we saw with NGINX. Once we ensured that, we moved ahead with benchmarking. We took a realistic load from one of our clusters, and we performed benchmarking tests across Istio and NGINX, where NGINX was our baseline. We gathered metrics like throughput, latency, and also resource efficiency to ensure that Istio is as performant. Once we ensured that, we moved ahead with the implementation. We changed our internal applications to deploy all the necessary resources onto the clusters. And also install all the necessary Istio components onto the clusters. And then finally, we started rolling it out. We started rolling it out across stage by stage. And after each stage, we ensure that we give enough soak time so that we get to detect any regressions or issues early. And finally, we also had a rollback strategy in case there are any client workloads that are sensitive to any kind of traffic disruption. We would have them switch over to NGINX beforehand so that they are not affected by this migration. To understand our rollout strategy better, I'm going to talk a bit about how our DNS mapping works today. So let's take a CNAME, right, like test.dev.bloomberg.com. So this is pointing to a DNS worker farm. Let's call it common workers. And this is a set of multiple it's a set of A records, and these IP addresses are coming from nodes across multiple clusters that are deployed across multiple data centers. For the sake of our example here, let's just consider we have two clusters, cluster 1, cluster 2, and each of the clusters is a set of nodes where you have workloads and NGINX controllers running. Now, this common workers would have the node IPs of all the nodes from both of the clusters which have NGINX controller running here. Now, once we decide to migrate to Istio, we do it cluster by cluster. We don't do all the clusters at once. So let's say we decided to migrate cluster 2 to Istio first. What we do is we create another set of nodes where we are running Istio gateway in an isolated fashion. And we would switch the cluster's node IPs from NGINX to Istio here. And then at this point, we have a hybrid setup where our traffic is being served by both NGINX and Istio. And this gives us a great chance to also compare the ingress responses across both the clusters and identify any issues proactively instead of waiting for the users to come to us. And once we ensure that things are running okay, we just replicate the setup of cluster 2 across all the clusters that we have. Now, about the rollback. So what we do is we also have another worker farm, let's call it common NGINX workers, which has all the nodes across all the clusters that have NGINX controllers running. And in case we determine one of the ingresses to be sensitive, we just migrate that CNAME from common workers to common NGINX workers beforehand so that they are not affected or they don't have to see any kind of disruption. So this is how the traffic would reach until the ingress gateways. Now let's look at what happens once it reaches the ingress gateway and how it reaches the pod.
Yeah, so let's take a look at how an HTTP request would flow from a client to an application that's running on BPaaS. So the client would first query our DNS system to get the list of node IPs where Istio Ingress Gateway is running. It would pick one of the IPs and send the request over port 80 or 443, depending on whether it's an HTTP or HTTPS connection. And the Ingress Gateway, which is running in host networking mode and listening on port 80 and 443, will pick up the request, and based on the host name and the request URL, it would forward the request to the appropriate backend pod. This all seems straightforward, but let's see what actually happens behind the scenes to make this possible. So we use Gateway API, and we deploy a set of standard resources, namely the gateway, which configures the listeners with the host name, and HTTP route, which configures the route to the backend service, and also a TLS secret, which stores the TLS cert for encryption. So Istio-D, which is the control plane of Istio, will pick up all these resources and then configure the Envoy proxy that's running in the Istio Ingress Gateway. And it would also refer to the Kubernetes service to fetch the list of pod IPs which are running behind the service. And apart from all these standard resources, we also create Envoy filters per ingress and also a global Envoy filter at the cluster level. We need these to customize certain HTTP configs which are not exposed through the HTTP route and the global mesh config, respectively. And finally, we also create a default gateway with wildcard hostname so that it matches any hostname. We need that for TLS encryption, where the client doesn't provide us with SNI information. We'll talk more about this in a later slide. So with that, we are done with all the images and diagrams. It's all going to be boring text from here on. So during our migration phase, we spent considerable amount of time ensuring parity between NGINX and Istio. And we expected our migration journey to be pretty smooth, but it didn't turn out that way. We encountered a bunch of challenges during the process, mainly because of the behavioral differences between NGINX and Istio, and also because of the various ways our clients use our platform. We'll talk about some of them today. So firstly, as we mentioned, our ingress controller is a shared resource. We imposed a 60-second idle timeout so that the connections don't stay open for a very long period of time. With NGINX, we had configured the proxy read timeout and proxy send timeout parameters to 60 seconds, which made sure that if there's any activity either from the request side or the response side, the connection would stay open. So initially with Istio, we had configured the per route timeout in the HTTP route to 60 seconds, but we didn't realize that it wasn't an idle timeout, but rather a hard deadline. And it would cut off the connection after 60 seconds, even if the server is streaming back responses. So we figured that Envoy's HTTP connection manager has a parameter called stream idle timeout, which basically resets the timer on any activity, and that's what we wanted. So we set this parameter to 60 seconds using an Envoy filter, and that's how we achieve parity here. And the next challenge is automatic retries on server-side failures. NGINX by default retries thrice on any upstream errors and timeouts. But it only does that for idempotent methods. Non-idempotent methods like post and patch were not retried. So with Istio, we had initially enabled 3 retries on 5xx error codes, which is server-side retries. But it did not matter if the error code was written by the gateway directly or by the application pod. So in the event when the request actually makes it to the application pod and that returns a server-side error, even the post requests were retried, which was not desirable by our clients. So we decided to revert back to Istio's default retry policy, which only retries twice on any transport level error conditions. And onward documentation also states that these error conditions are safe to retry and the request wouldn't actually make it to the application pod. So although we couldn't replicate the exact same behavior as NGINX, it felt like a safe compromise for us.
Next thing was we had a lot of client applications relying on default redirect behavior of NGINX. So the default redirect behavior is when you enable proxy SSL redirect in NGINX's configuration, and when HTTP traffic is sent out for an HTTPS ingress, it's automatically redirected with 308 redirect code. This was something that we couldn't directly enable using any configuration on Istio or Envoy. So what we did instead was, for every HTTPS ingress, we created another HTTP route which defined a redirect filter. And this redirect filter would send a 301 response code. We chose 301 because Gateway API didn't have support for any status codes other than 301 and 302. 301 seemed like, because it says moved permanently, we thought it would be similar to 308, but that was not the case. Some of the client applications that relied on libraries like Python requests would not respect the originating request method when they receive a 301, which means that a post request could change into a GET upon the redirection. So this was not desirable for us. So what we did was, in this same redirect HTTP route that we created, we added another response header, and we added a Lua script to our global Envoy filter that Sahil mentioned, which inspects this response header and converts the status code from 301 to 308. This is to ensure that we are only converting the status code for the redirects that are initiated by our system and not by the client code. So yeah, that's how we ensure that the client behavior doesn't have to change in this case. The next thing was, just to give some context, we have applications that traverse through multiple proxies before the requests reach our ingress gateways. And these clients rely heavily on the X-forwarded headers to either distinguish where the traffic should be, how the traffic should be processed, or to reconstruct their redirect URIs once the traffic reaches their pod. Again, NGINX behavior, very straightforward. You could just set use forwarded headers, and NGINX would automatically send all the X-forwarded headers like for, proto, port, and host by default. But in Istio with Envoy, we didn't have a direct configuration again, so we initially started off with setting the X-forwarded host and port, because those are the headers that our client applications rely on the most, ourselves using the connection information. But we soon realized that this was using the immediate connection information and not the originating client connection through the proxy. So what we did was we dove deeper into Envoy docs to see if there's anything that we can find, and we found not one, not two, but 3 configurations that we could set to achieve what we wanted in terms of X-forwarded headers. This again was to ensure that the client behavior doesn't have to change when we migrate.
Yeah, again, because our ingress controller is a shared resource, we also enforced a 1 MB limit on the request body size. So with NGINX, we could directly set it using the client max body size parameter. But with Istio, we had to create an HTTP buffer filter to cap the payload size to 1 MB. And later we realized that this filter was actually conflicting with protocol upgrades and in turn impacting all the WebSocket connections. So WebSocket basically uses protocol upgrades to upgrade an HTTP connection to a WebSocket connection. And Envoy also states that request buffering is not compatible with protocol upgrades. So we fixed this behavior by basically skipping the buffer filter whenever the request contains upgrade WebSocket header, which is an indicator for WebSocket protocol upgrades. And sanitizing the URL that is sent by the client before it's forwarded to the backend service is another aspect where NGINX and Istio showed differing default behavior. NGINX by default merges consecutive forward slashes in the URL. And it also decodes certain special characters like forward slash and backward slash before it forwards it to the upstream. You can see that happening in the example here. And Istio displayed the exact opposite behavior, but we figured that it also has a parameter in its global mesh config called proxy path normalization, which we set to decode and merge slashes. And as the name suggests, it would merge the consecutive slashes and also decode the special characters. Yep. And we also host a bunch of web applications on BPaaS. So in order to reduce the response time, we had enabled gzip compression. With NGINX, we could directly set the use gzip parameter to true, and that's it. But Istio did not have a straightforward way of doing this, so we had to, again, create an HTTP compressor filter with gzip compression and set all the configs so that it matches that of NGINX. So far, so good, but there's one small caveat here. So the client can indicate if it can handle encoding using the accept encoding header, and when it's set to star, NGINX doesn't treat it as wildcard and would not compress the response, but Envoy does, and it would compress the response sent by the upstream. So in order to fix this, we again created another Envoy filter, which is essentially a Lua script, and that would rewrite the accept encoding star header to accept encoding identity, which would instruct the gateway to not compress the response.
So we host a diverse set of applications on our platform, and we do have a lot of legacy applications running. And some of these applications actually use HTTP 1.0. Again, the behavior was contrasting. NGINX would accept the traffic, and Istio Envoy by default rejects any traffic with HTTP 1.0. So with a 426 upgrade required error. So what we did was, again, went through the documentation, found this variable Istio meta HTTP 1.0 that you can set in the ingress gateway configuration to let the traffic flow and not get rejected. The other thing that we briefly talked about during traffic behind the scenes was when clients send no SNI. Some of these legacy clients, again, do not send us any SNI information. And NGINX is very gracious in such cases. It just presents a default or a fake certificate by itself and then ensures that the TLS handshake is complete and the routing is proceeded. But Istio requires on a strict SNI matching. It just fails the connections without an SNI, and because the gateway doesn't know which certificate to present. So to overcome that, what we did was we created a catch-all gateway with a wildcard host on our end, which would just have a default cert, so that client applications that do not send an SNI would just complete their TLS handshake using this default cert, and the routing is done based on the host header of the request. Along with all of this, we also came across an interesting Istio behavior during our migration. So to give an idea, we had about 250 gateways and about 400 HTTP routes running on our cluster. We had a reconciler that would reconcile these resources periodically. And what we noticed was occasionally the user ingresses would fail with a 404. And this 404, at that time, we initially thought it was a blip, and then we started noticing it more frequently. And this issue is self-healing. Like, it would last from anywhere between seconds to multiple days. So we started digging into it. We first looked at the gateways and gateway resources and HTTP routes to see if something was changing during that time. But we saw that nothing was rejected, nothing was corrupted. We looked at gateway to see if anything stands out, nothing. Then we finally enabled debug logs on IstioD, and I can just walk you through what we found. So if we follow along the highlighted red section, let's say we are configuring testapp.abc.com, and it's being set up for the HTTP protocol. So you see the port number is fine, protocol is good, host is good. This is what is being merged with the gateway. The host seems perfect, which is all good. Now, when we move to the HTTPS configuration, we saw that the port and protocol were 443 and HTTPS, great, but the host was truncated. And this truncated host was what we were seeing was being merged with the gateway, and this immediately is followed by this default 404 setup error. Initially, we thought this could be a cosmetic log issue, but we also noticed that this was the configuration that was being passed on to the gateway. So we raised an issue with the Istio community, and they quickly reverted and fixed this issue. It happened because of a multi-threaded workflow was trying to modify a shared object. There are more details in this issue. If anyone's interested, they can check it out. But with that, I think some of the things that worked for us during this migration were having an easy rollback option, so that in case we detected any use cases that were not readily supported or any regressions, we could easily switch users back to NGINX. And having that comparison dashboard during the hybrid setup was very helpful, so that we could proactively detect issues instead of relying on users. Some of the pitfalls that anyone embarking on this journey could avoid is checking the existing NGINX, checking the existing ingress controller configuration more thoroughly. We did that, but there were other customized configurations that were deeply buried, which led to all the challenges that we spoke about. So that's something that we should go through. API documentation, again, maybe the first couple of lines that are said in the documentation are straightforward, but then there's more nuances hidden deeper into the configuration. So that's another thing that everyone should go through. Finally, our recommendations, again, having an easy rollback option, can't stress enough, it's very important. Versioning Envoy filter changes. Envoy filter is very sensitive in the sense that if smallest of the misconfigurations could just destabilize your entire mesh, we ourselves ran into it multiple times. So having some kind of versioning on that is very, very important. And then again, monitoring your traffic, use all the logs, observability tools like Grafana, Kiali, Prometheus, whatever you use to detect issues early. And finally, having well-written runbooks to help during upgrades or troubleshooting so that it's easy and you're not, this kind of information is pretty volatile, so it's important to note it down somewhere. But yeah, with that, thank you so much. I hope you took away something today.
All right. Let me grab this one in the back. Is Mike live?
How did you find observability between Istio and NGINX? Like, was one better than the other? Or?
You mean in terms of performance?
In terms of like, were the default metrics better in one versus the other? Did Envoy make like structured logging and things like that? So like user experience, less so performance.
There's not much of a difference, I would say. Also, I would want to stress that we are using Istio only as an ingress gateway currently. We're not using the mesh feature of Istio. So I would say that it was not much of a difference between the NGINX ingress controller and Istio's observability. Yep.
Was there any performance gain because you migrated from NGINX to Istio?
Right. As we mentioned during our benchmarking phase, we noticed that for the same type of requests, Istio, like Envoy, was able to handle a lot more requests per second compared to NGINX. And also with differing payload sizes, Envoy was able to handle a lot more throughput than NGINX. So yeah, we noticed some performance gain when we moved to Istio.
When you ran into the hostname truncation issue, how long did it take you to realize this is an actual bug we need to file an issue for? Like, did you spend a lot of time thinking there's just a piece of documentation we haven't read, or was it something you were pretty early on when we need to file a bug?
Yeah, so we were initially doubting our setup and our cluster resources that were being created, because obviously we were like, oh, this can't be a bug on their end. This is definitely us doing something wrong. But once we enabled the debug log, because there's a lot of logging once you enable debugging, right? So it's very difficult to follow along and highlight the pieces that you think are problematic. So once we did that, we waited for this issue to occur 5 times. And then we filed an issue to see if anyone else has faced this. And initially, they kind of said it's not, they are not doing anything in terms of truncating intentionally, but somehow later they figured out that it was being done because of the way the code was written.
Hey, thanks for the talk. It was really good. Wondering, during your evaluation phase, did you look at other ingress controllers, and what made you land on Istio versus the best other options?
Not really. We actually were looking at Istio because we had other plans with Istio moving forward in terms of L7 policy control and authorization. So we wanted to make Istio work, which is why we started with looking only at Istio.
Awesome. Thank you so much again. And let me get one more question over here. We'll turn you loose. I actually really enjoyed the point that you described where you were like looking at the logs and you're like, surely this is a log problem.
Yeah.
Oh my gosh. What a moment.
Yeah, kind of a two-part question. The first is just kind of yes or no. Is this an entirely self-managed Istio instance?
Yes.
And second, what is kind of stopping you guys from using like a full mesh scenario, whether that's like sidecar-based or ambient?
So currently, because of the way our DNS system works, so all the like host names are actually registered in our internal DNS system, and if a service wants to reach out to another service, it has to make a DNS query, and then that resolves to our node IPs where Ingress Gateway is running. And it's just because of the way our DNS system works currently. There's no pod-to-pod communication directly right now. And yeah, that's what we want to move to, and Istio would help us get there.
Awesome. Thank you for taking the questions, and thank you for your presentation.